Can people hear me? Thumbs up. Okay, greetings Aeolianists. Welcome everybody. My name is Jean Ellis. For those of you who don't know me, I am a faculty member at the University of South Carolina. I also moonlight as an amateur custom Zoom background artist. For those of you, one is available upon request. These are pictures of our guest speaker. He's imbibing in the one above me. Sorry, Doug, I just had to do this. Please don't be mad. It is great to see so many friends and colleagues out there. It goes without saying, and I hope everyone and their loved ones are staying safe and staying healthy. Before we go any further, a quick reminder on etiquette. Stay on mute for the entire duration of the presentation. The speaker will accept questions at the end of the presentation. You can add these in the chat or you can ask them orally using your Zoom hand. Lastly, on the announcements, the Zoom meeting was scheduled for 2 hours, but our speaker has a meeting after about an hour and a half. So please be aware of that. Sorry for the scheduling snafu. I want to start by thanking the ISAR board. It is the intent of the board to hold a regular series of online meetings through 2021. They have asked me as the chair, I guess, of this session to solicit you for suggestions or nominations from early career researchers, research clusters, research networks, and individual. The ISAR board aims to offer talks across the diversity of our membership. The board is really grateful to the speaker today for, quote, breaking the dust. Thank you, Mike Hilton, for that one, on this new way of communicating. So our guest of honor today is the Professor Dr. Sherman of the University of Alabama. Look how happy he is out there. He told me not to introduce him and to ask you, quote, to turn off your video and turn off your sound and come back in 45 minutes, unquote. Doug, I'm sorry, people aren't going to do that. We actually want everyone to keep videos on if you can do that, just because we are really happy to see everyone's face. Keep the mute buttons on. And also, Doug, please behave yourself. A lot of your academic grandchildren are on the line, so be nice. For those of you who don't know, I am one of Doug's former PhD students from a long, long, long time ago. So I believe that we all recognize Doug's contribution to the Aeolian coastal and geographic communities. It is really hard to encapsulate and briefly introduce a 40-year career. I meant 4 because, you know, Doug can't quite possibly be that old. But I'm going to be super brief only because you guys came here to listen to him and not me. Career items of note include that he is a fellow of the American Association of Geographers and a multiple Fulbright scholar. He is a leader represented by, for example, his tenure as the current or former head of 3 geography departments in the United States. He was also a former Sea Grant executive director. He was an outstanding and is an outstanding advisor and a prolific and beautiful writer, and is the author of over 100 papers. We are here today to listen to a presentation that I believe represents a summation of a lot of his work within the Aeolian sector, and it's titled Deconstructing Q, the Empirical Barriers. And with that, I will pass the mic to you, Doug. Thank you for doing this today.
It's my pleasure, and thank you for that introduction. I really appreciate it. I don't know where you got some of those photos. That's an interesting collection. I'm pretty sure that I was photoshopped into several of those.
Sure.
So I'm going to jump right into this and share my screen with you guys. You know, despite how Jean put this so eloquently, basically you get asked to do these kinds of presentations when you're closer to the end than the beginning. And clearly that's the case for me. But this is a theme that has occupied probably way too much of my time and attention over the last several decades. And it's kind of a neat opportunity to get to share some of these things with all of you, and then hopefully get some feedback from you when we're done to help outline some next steps as we try to understand how to deal with predicting windblown sand transport. So I guess what I don't know how to do is change. Here we go. So let's start with a simple question. Why study windblown sand? And there are a lot of reasons that resonate with us for different reasons. One, it's a physically interesting problem. We can stand out on beaches, for example, and see the sand blowing by our feet. Blowing sand represents a fundamental geomorphic system. In fact, in many senses, other than purely gravity-driven systems, it's one of the simplest geomorphic systems. Blowing sand is important for the evolution of many terrestrial and extraterrestrial surfaces, Mars, Venus, Titan, maybe Pluto, but in a different sense. And we don't know what it's like in other solar systems. There are a lot of resource issues and hazard issues associated with blowing sands. Finally, it's just a difficult problem to deal with. And for a lot of us, it's that challenge of trying to reach another level of understanding about something that's a commonly observed process. Gregory, in his 1998 book, and I can't vouch for the truth of this, but I like the argument, argued the transport potential of wind is greater than that of any other fluid system, greater than all the rivers, glaciers, and waves and tides of Earth. And of course, he used the word potential because a lot of the surface is not open for aeolian processes. But here I've got just a sample. This is a Google Earth image of the Taklamakan Desert, where you have a basin 900, it's actually a bit more, 900 kilometers long of basically unvegetated sand. And this is a highly mobile area. This is actually one of the source areas for the dust that often plagues Eastern China. Now, as I said earlier, blowing sand is a simple geomorphic system under quote unquote ideal conditions. And I'll talk about those in a minute. Unidirectional flow. Like many of us, I began my career studying sand transport in the surf zone, where we had combined flows of oscillatory motion under waves and tidal flows and longshore currents. This seemed pretty simple compared to that. It's physically accessible. If we were studying the windblown sand at this location, we could stand out there, deal with our instruments, put traps down and make our collections. Unlike many other transport systems, the ranges of sand sizes that get moved are relatively limited. And transport is mainly as saltation. So again, when we're dealing with sand, we're not particularly concerned with suspension. Now there is a complex feedback, several of them, between sand and wind, but we're going to put those aside for now. These are the characteristics of an idealized aeolian sand system. Now I used idealized because in truth, there are no purely ideal systems. And these characteristics are relatively well represented in most wind tunnel studies, seldom in the field, where we have a flat, horizontal, unobstructed surface, uniform size, cohesionless, at least semi-spherical sand grains, fully developed turbulent flow, where we have a boundary layer that's thick enough that our wind instruments are inside of it, and uniform steady wind, also something we know is not quite true. So for these conditions, these are the conditions that the sand transport models that predict Q are designed for. Why is this important? You guys maybe not be able to see this past that view. Q is the sandwich, as I'm going to put this, for dune building. And it's based on this fundamental proposition by Brunson and Thorns. And I love this statement. For any given set of environmental conditions, through the operation of a constant set of processes, there will be a tendency over time to produce a set of characteristic landforms. In the case of this conversation, We're talking about the processes that drive aeolian sand transport, and the landforms that we're looking at principally are dunes. Our Q sandwich looks like this. The rate of transport of wind-blown sand is a function of the wind speed, the grain size, D, rho S, sediment density, rho, the air density, and G, the gravity constant. In real life, we can throw in a lot of complicating factors, but essentially it comes down to this. Now, this is a Reuben sandwich. This is one of my favorites. If I go to the same restaurant and I order this sandwich over and over again, I know what the ingredients are and I know what it should taste like. But if I go to a restaurant and I take a bite into that sandwich and it doesn't taste right, the first thing many of us do is kind of peel it back to make sure all the ingredients are there. That's deconstructing the sandwich. So Reuben, as you can see, should have 5 ingredients. Coleslaw or sauerkraut, a Russian dressing, rye bread, Swiss cheese, and corned beef. So we know what should be in the sandwich. If we peel it apart and all those ingredients are there, and it still doesn't taste right, then the recipe must be wrong. And it's about the recipe for sand transport that we're going to talk about today. When we look at our models to predict sand transport and we look at this very simple expression, all the ingredients are there, but it doesn't taste right. So what's wrong? Some of you who've known me for a long time will remember when I used to show this kind of slide routinely. First of all, sand is stupid. It doesn't know what it is or what it's made of, doesn't know how big it is, doesn't know where it is or how it got there. Sand doesn't know what time it is. It's passive. It's non-motile, means it can't move by itself. And to the extent that it can have some sentience, sand obeys laws unthinkingly. Wind is similarly stupid. Doesn't know what it is or what it's made of, doesn't know how fast it is, doesn't know where it is or how it's going, doesn't know what time it is, and it also obeys laws unthinkingly. So that leaves us with our last element here, is our science stupid? Now, I'm not talking about the scientists that are studying these processes. Some of you guys are the brightest people that I know. It's how we as a community approach this. So let's go back to some basic propositions. Science is the pursuit of systematic and formulated knowledge. Oxford English Dictionary. And implicit in the practice of science are the concepts of observation, methodological rigor, and skepticism. This is the empirical part of this presentation. So how do we begin? Let's look at what are considered to be some of the hallmarks of science. And one of the first is the reproduction or replication of results. I've got quotes here from 2 highly cited sources on this information. First, I want you to note that their definitions of reproducibility and replicability are in fact exactly opposite of each other. So let me take them in turn. Drummond says that we should aim that we can reproduce results, that is, conduct a different experiment with the same theory and get the same answer that somebody else did, or we can replicate step by step the experiments. And he stated, reproducibility requires changes. Replicability avoids them. Although reproducibility is desirable, the impoverished version, replicability, is not one worth having. So basically the idea here is that we want to get the same answer as someone else with the same covering law. I'll talk about that in a bit, but we don't need to go step by step through their recipe. Now, the National Academies of Science, Engineering, and Medicine claim the opposite, that you want to reproduce experiments step by step to verify the results, or you can replicate results through another approach. And the key here is when scientists cannot confirm the results from a published study, to some it's an indication of a problem, and to others it's a natural part of the scientific process that can lead to new discoveries. We have a challenge that for the most part, we cannot or do not replicate or reproduce results. And part of the issue is one of commensurability. The word commensurability is one of my favorites. Actually, incommensurability is even a greater favorite of mine. It refers to the ability to compare the results of one experiment, ostensibly to measure one thing, with another experiment. I want to point out a couple of examples of this being addressed in the literature. A great paper by Barkan et al. About 2 quotes from that. Progress in some areas of process-based aeolian sediment transport research is hampered due to a lack of reliable comparison methods, i.e. lack of protocol, lack of standardization. And more importantly, they go on to say, measurements made without a reliable framework of comparison are case studies. They are not contributing to this body of general knowledge except as what can be considered to be ideographic approaches. It's not quite as simple as that, but that's kind of the reductio ad absurdum. Martin et al. Talk about a specific example of this. Observations of saltation by natural winds depend significantly on the time scale and the method used for determining shear stress and sand flux. In other words, if we don't have protocols that dictate how we measure shear stress and flux, then we have the potential to measure substantially, or in terms they use, significantly different outcomes. Not that the natural system is changing, our detection of that and our representation of it changes. We have this quote from Ellis et al. And this is a specific application of protocols. The lack of a standard protocol for the measurement and analysis of vertical mass profiles for aeolian saltation, should be an O there, precludes replicability. And I'll make an addendum here, except by accident. Sherman et al., the characterization of intermittency, this is another saltation characteristic, will reflect both the nature of the phenomenon and the experimental methods that were used to characterize that. Again, if we don't have protocols, we cannot presume a standardization. Now at this point, shouldn't there be some equations or pictures? Here's a picture. Wet desert. I want you to get a sense of these sand dunes. I don't have a cursor on here, but that kind of big bullseye in the lower center of the photograph is just under 1 kilometer across. I would like you to think about how many grains of sand are in these dunes. I'd like you to understand that every one of those sand grains was moved individually by the wind. And now that we have an interlude, I told Dr. Ellis that I would put in this plug for AAG abstracts. This is a shameless plug for the American Association of Geographers. If you have more information, please feel free to contact Jean. Her email is below here, or Christy Swan, whose email is also there. Registration is still open. There are virtual and in-person sessions. There are competitive rates for students and AAG members. I'm happy to answer more questions about that when we're done. Okay, back to this. Some fundamental attributes to try to deconstruct how we approach a problem. And there are 4 terms that are relevant here. Deduction. The phenomenon, in this case Q, is a logical consequence predicted or deduced with a covering law if initial conditions are known, or in the languages of logic, if we understand the premises and they are true. The covering laws we have here are essentially Newtonian mechanics and boundary layer theory. Covering law includes one or more elements of natural law and describes relevant initial conditions. If we have a covering law and we know the initial conditions, we can deduce the answer. And in fact, from that premise, there can be only one answer. If this, then that. So, and then empiricism, the search for knowledge based on observation or experience. Most alien geomorphologists that I hang out with are empiricists. We're observationalists. We either do research, observational research in wind tunnels or in the field. And if you've done enough of the empirical work, error will be your friend. Now, the term error usually has a negative connotation. I'm using the term error here to refer to any unanticipated answer. When you have a transport rate equation with an equal sign in it, and it doesn't equal, that's an error. Error is not inherently bad, and there are lots and lots of quotes about error. I picked out a couple here. Truth emerges more readily from error than from confusion. Francis Bacon. Now, I use this quote from Bacon here, not because it's particularly the best quote, but Francis Bacon is the father or grandfather, or whatever we want to call him, of the quote unquote scientific method. For those of us who are skeptical about the scientific method, it's worth recalling that Bacon was a lawyer, not a scientist. And anyway, in any science, any unanticipated outcome can be considered an error and then potentially worthy of investigation. Error should motivate us. Karl Popper, famous philosopher of science, wrote, "The history of science, like the history of all human ideas, is a history of irresponsible dreams, of obstinacy, and of error. And science should be visualized as progressing from problem to problem." Now, many of Popper's philosophical views have been refuted or at least debated heavily in the last half century or so since he wrote, but few argue about this kind of statement. Then we have an analogous quote from Preston James that understanding progresses from error to error. So what does it mean for us? Every meaningful scientific/empirical model of a natural system is to some degree erroneous, and I'll put here parenthetically, at least in its application. That means that when we're working in the natural world and we're trying to measure these, our measurements never give us the exact answer that we're looking for. Some errors are trivial, others are critical, and much of the operation of science concerns the distinction between trivial and important. Three types of error for a simple term: errors of theory. I'm really not going to address those today. Errors of measurement, and these deal with the indeterminate errors. Those are just random errors that should average out with a large enough sample size. And bias or systematic errors, where we have something wrong that causes an offset in all of our measurements. And then we have errors of method, and these can be of many sorts. Another quote by David Harvey: "The ideal situation, of course, in which is one in which the magnitude of the error involved is so small, it can be ignored for our given purpose." I like this paper by Alchin 2001, where he came up with a taxonomy of errors, and it helps us approach how we study any kind of system, in this case, wind-blown sand. An error is any mistaken conclusion or unintended outcome in science. And here I'm focusing on two types: the material errors and the observational errors. The material error, and these are all empirical. The material errors are improper procedures or the perturbation of phenomenon by the observer. The observational errors are those that are associated with environmental constraints, insufficient controls, the instrumentation limits, or the lack of protocols. This image used to be one of my favorite challenges to audiences and to classes, and that is to guess where that is. If you already know, please don't share. We'll have a chance for prizes, not really, at the end of this presentation. Now, I don't know if Andreas Boss is on, but he teased me about this quotation, but I think it's relevant here. This is a quotation from Donald Rumsfeld, who was a former US Secretary of Defense, and it's a reminder to all of us. There are known knowns. These are things we know that we know. There are known unknowns. That is to say, there are things that we know it's hard to read this. There are things that we know we don't know, but there are also unknown unknowns. These are the things we don't know we don't know. Whew. What we know, or we believe we know, about the fundamental Aeolian sand transport hypotheses, again, under ideal conditions. First, as I said before, that Newtonian mechanics and boundary layer theory are suitable for the problem. Second, that the driving forces depend on the properties of the air, and the resisting forces depend on the properties of the surface, the sediments, and gravity. And if we can constrain the driving and resisting forces, those set up our initial conditions, or those are our premises that we can use to test the theory based on mechanics and Newtonian mechanics and boundary layer theory. So here's our first non-tasty Q sandwich. And there are a lot of versions of this diagram, some newer than this, and some include different models. That's not the point. We have a collection here of some of the most often used sand transport equations. All of these models include the same basic variables. And on the x-axis here, we have shear velocity, the representation of wind. On the y-axis, we have Q, the sand transport rate. Now, I've looked at this diagram for a long time, and it's hard to explain why there is such a large degree of variability. Think about this. With the exception of the L'Hotel model and the Bagnall model, because those two combined lab and field data, these are all lab models. And we presume that the results of their experiments were fit by the use of empirical constants to replicate as close as possible, or reasonably as possible, their measurements. But what you're seeing here in the spread in these curves is not theoretical error. That is, in fact, all empirical error, because no matter how the models are composed, for a given shear velocity, there should be a given sand transport rate. So this spread has to reflect issues with the experiments. Now, there are a bunch of things involved in explaining what those errors can be. One is that many of the wind tunnels are not long enough for fully developed transport, whether that's an issue of fetch length or the saltation cascade length or the saturation length. I don't know. And to the best of my knowledge, with the one exception of the research that Bruce White did in his the Planetary Aeolian Lab wind tunnel to replicate transport conditions on Mars, where his results were very similar to those of Kawamura, no one has tried to really replicate these experiments. And we know, the fetch length, saltation cascade length, saturation length all deal with the length of the wind tunnel. Sidewall effects have to do with the width of the wind tunnel. For example, Kawamura's wind tunnel that he put literally hurricane force winds through, that wind tunnel was 5 centimeters wide. What are the data trying to tell us? Now, John Southard was the preeminent sedimentologist of his day, process sedimentologist anyway, and he gave a series of short courses. The notes for some of those short courses are classic. Bernie Bauer and I, sometime in the mid-90s, were privileged to attend one of these short courses. And Southard made reference to a couple aspects for data analysis that I've never forgotten. One is, if we believe that we have the physical model correct, then any scatter in these diagrams like this has to be either an unknown factor or experimental error. If we know all the factors, then that is experimental error. The other thing is that if we have an intercept that should go through zero, but doesn't, we have some form of bias error, right, that prevents the intercept at the origin, or we haven't fit the proper curve. Now, in this example from Nick Lancaster's work, this is a really great study. We have a dune shape factor on the x-axis and a speed up factor on the y-axis. As the shape factor gets smaller, in fact, approaches zero, basically the size or the shape of the dune essentially gets flat. And so as that shape factor approaches zero, the mean speed up, in fact, should go to zero. Now, it doesn't, at least in a linear fit. Maybe this is an exponential function that goes to zero or dives toward the intercept. I don't know. But it means that we have an empirical problem here, solvable by more data or better data. Here's an example specific to transport. The open dots represent a plot of observed versus predicted transport rates using the Littau and Littau 1978 equation. You can see there's a fair amount of scatter, and you can see, if you look carefully, the slope of that best fit line is about 5.5 to 1. So a substantial over-prediction of transport. One of the things that we did in this study was recalibrate a bunch of transport rate equations, including the Littau and Littau model. And based on some of the work of Bailiang Li and his compatriots, we use an apparent von Karman parameter rather than the von Karman parameter to calculate shear velocity. And that gives us the relationship shown in the black dots. This is one aspect of recalibrating models to improve the empiricism. That line is a one-to-one slope. So we have a better representation of transport rate if we are allowed to manipulate the original models. They're still scattered though. And if we look at that corner, we see this. At small transport rates, we have a substantial bias in these measurements. None of the observed transport rates are as large as the predicted transport rates. And the largest relative errors here are close to the threshold of transport, U star T. Here we have two types of problems. We have empirical issues with actually measuring what the threshold shear velocity is for given conditions. And we have definitional / theoretical issues in that there is no universally agreed upon definition for how we recognize the initiation of transport. This is baked in to part of the bad taste in our Q sandwich, because almost all of those models that I showed you represented grain size with the threshold shear velocity. Here's another example. Here we're looking at ripple migration rates And these are dimensionless ripple migration rates relative to a dimensionless shear velocity based on wind tunnel studies. And we're looking at the results of 4 different studies here. Borsey, 1973, that is the one that includes the greatest excess shear velocities. He had an odd wind tunnel. It was very low, and he blew some really fast wind through it. So his results are a bit different. We have the data of Andreotti et al., Zhu, and Cheng et al. And we can see that those data sets roughly parallel each other. So they're measuring the same structure of relationship, but they are all offset from each other, which means there's some internal scaling issue that the dimensionless representation doesn't address. The dimensionless representation should calibrate all of those, and in an ideal world, those lines should fall on top of each other. Then we have this. The red data here is a compilation of all of the field data that we could find in our 2019 study, including some original data that had a reasonable representation of shear velocity and ripple migration rate. And although we have kind of a big ugly blob down around U star over U star T is 2, these curves are nowhere alike. And so one of the other issues we face is this fundamental observation repeated in lots of experiments that the field relationships that we find do not match the wind tunnel relationships that we find. The fact that we can fit regression curves successfully is important, but the scaling is very different. Here's another issue in Q. This is from a paper, Zhang et al. In Review, where the data sets from field studies, including some ripple migration studies, are plotted a dimensionless creep transport rate on the y-axis and dimensionless shear velocity on the x-axis. Now, Bagnold tells us that this value should be relatively constant at about 25%. And you can see there is a dot off on the far right that is about 25%. That's his point. You can see there are a bunch of symbols at 3 or 4 or 5% transport rates. These indicate essentially no relationship. That's what Bagnold's data should also tell us, that the proportion of creep transport is about constant with shear velocity. But most of the others, the data of Hijma and Lauder, Liu et al., and Han et al. All show, sorry, I'm trying to find the Liu et al., all show some form of slope, showing that, in fact, this isn't a constant value. So we have fairly well constrained experiments that give us substantially contradictory information. And even to the extent that it's not contradictory in terms of whether there's a trend or not, the absolute values that we're seeing are also substantially different. So here's an empirical challenge. We often recognize 4 modes of transport: creep, reptation, saltation, and suspension. Many of us define reptation and creep as being 2 parts of the same thing, i.e. creep. However, empirically, and please correct me if I misunderstand that, there is no way we can actually separate saltation from reptation from creep. Even creep at the slowest, if we say it can't leave the bed or it has to leave the bed, if you look at these diagrams, as grains roll over, unless they're perfectly spherical, they will leave the surface. We can't actually measure a distinction between these. We can categorize core characteristics. In water studies, everything not suspension would just be called bed load. And maybe that's what we should do as well. Now, the last visit of our Q sandwich. And I'm not going to say anything about the last two characters, sediment and air density, and the gravity constant. We know that they vary a little bit, but they don't vary very much. And those are things that can be taken care of as kind of the second order corrections. But the first three, Q, U, and D, are the big problems. We don't have a universally adopted protocol for how we measure sand transport. We don't have a protocol for what conditions, and by the way, I'm just looking at the field, for what conditions are acceptable. How long does the fetch length have to be before we believe that we're measuring saturated equilibrium flux? What about acceptable trap designs? Some of the older traps that we used to use had exceptionally poor and non-constant efficiency. What about the horizontal variability in transport? Study after study, setting up traps adjacent to each other has shown that we can have, depending on the time scale, 25, 50, 100% sand in measured transport rate with the same trap over 1 meter separation. What's the real value? That's one set of problems. Wind speed. And basically, when we're talking about wind speed, we're talking about shear velocity, the derivation thereof, because that's what we use most often. We have differences in anemometry, good, bad, or ugly. And it's seldom that we compare one instrument with another, or it's seldom that we actually compare one instrument with another of the same kind in the field. How about deriving shear velocity from the Reynolds stress equation versus the law of the wall? The law of the wall tells us that in a well-developed boundary layer, there's a constant stress layer where U star remains the same value. And that value, we used to believe we could replicate with a Reynolds stress derivation. But the work of Andreas Boss and others has shown us that the Reynolds stress derivation from ultrasonic anemometers is not vertically constant within what we used to think was the constant shear level. And basically, that means we don't know what we're doing anymore, which is a frightening and unsettling concept. And finally, with grain size, this is something we tend to overlook. If we take the same sand sample and measure it with different methodologies, sieving versus laser scanning, for example, we get different measurements of D. Let's say that they're the same. We don't actually know how size and shape distributions influence transport rates or the threshold condition. And there's been virtually no work on that other than to say, we know that we do. We know that the shape distributions, for example, influence fall velocity. And fall velocity is one of the metrics, or a surrogate, if you like, for shear velocity in reaction relative to U star T. So that's kind of taking a look at the components of our sandwich that we don't like. Now, I don't really have a conclusion to this presentation. And because I'm looking at my screen, I can't actually tell if any of you guys are still there. Hopefully some of you are. A philosopher of science, Shakur, wrote, "Through thousands of errors, we reach the truth." Now, I don't think we've made 1,000 errors in our study of alien sand transport, but we've made our share. And I hope that, and I know that many of you guys have experienced the same frustration, and we've learned from them. Elucidating errors and recognizing which ones of those are important is a necessary precursor to avoiding them. So to finish, I want to some acknowledgements. I want to acknowledge the organizers of this, especially Mike Hilton and Graziella Miat de Silva, who knew exactly how to find my weak points, i.e. my ego, and get me to accept this. I also want to give special acknowledgement to my many colleagues over the years who have taught me a lot of valuable lessons about the way to do field experiments and the way windblown sand works. And that goes back to my mentors when I was a master's and PhD student, Carl Nordstrom and Brian Greenwood taught me a lot about field work. Bernie Bauer, my longtime colleague, Paul Garris and others, you guys know who you are. I didn't want to start going down this list because I'll leave somebody out, but I've learned more from you all than words can ever state. And to any degree that I've learned something from this experience, it's because I've been able to learn from you all. So, any questions?
Thank you, Doug. I don't know if you can see everyone clapping their hands. I'll let you moderate your questions. Is that okay, Doug?
Yes, I do want to ask this first question. Does anyone want to take a stab at that field location with those beautiful white sandy? Robin, you can't answer because I know you were there. I don't know if...
I know the answer, so I'm out.
Bernie's there, so you can't answer either. Anyone want to take a shot at that? Bernie or Robin, do you want to explain the circumstances of that beach? Help me out here, guys.
Go ahead, Robin. I'm assuming it's a Jerry in Brazil, but at least what I saw.
No,
Maybe
that was
maybe Robin
did,
wasn't there.
we did an experiment in the around 1996, I think it was, and around mid 90s, and we picked, as we typically do, places that are supposed to have howling winds and nasty weather to improve our chances of getting aeolian transport. And in this case, we had followed up on a collaboration that started with Bill Carter, who unfortunately is deceased, and one of his then PhD students who was recently graduated, Derek Jackson, who now has enjoyed an extraordinary career in Ireland at the University of Ulster. And so here we are in County Donegal in, I think it was February or March, when it was supposed to be just nasty weather. And for some reason, wherever we went for a series of experiments over about 15 or 20 years, we invited high pressure systems coming in extraordinary weather patterns that weren't supposed to be there. And so here we are in Ireland, where it's supposed to be, wet and nasty and windy. And it turns out we had 2 to 3 weeks of extraordinarily sunny weather, very mild, and all the Irish locals in the area would come down to the beach, partly to see what we were doing, but partly to enjoy the sunshine. We'd see them walking out on the beach early in the morning, and then coming back late in the afternoon, beet red, like lobsters, because of the extraordinary sunshine they'd been exposed to. So that was Ireland, Innisfree Beach.
Yes, I remember well now, and especially the lobster-looking Irishman coming back at the end of the day.
It's since been renamed. The beach has since been renamed to Reuben Beach, I believe.
To Reuben Beach?
Yeah.
Oh, got it. Good one. So any questions, guys, or do you want to get on with your lives?
Doug, I do have a question, and it's more of a conundrum that I think that you've posed, which is you seem to be suggesting that errors are a good thing. And so we make science proceed over the long term by making our fair share of errors and learning from them. And yet on the other side, you're arguing that we need protocols of various sorts, rigid protocols, which then may constrain how we go about doing our science. And so can you sort of comment on how those seemingly disparate ideas can be put together?
Sure, that's a great question. Errors are inevitable in natural sciences, right? And as I pointed out, a lot of them are trivial enough we can ignore them. But even going back to the notion of Kuhn's scientific revolution, where we accumulate anomalies. You get enough of them, those are errors, that you change theory. So we can expect this. The establishment of protocols, though, allow us to see if we're all making the same error, or if the errors are just because we've done things differently. And even the adoption of a protocol, if we look at other sciences, protocols evolve as well, but they evolve by comparison. These guys do it this way, and so we'll do it this way, and we'll have a control and do it their way as well. So we can compare our protocol with their protocol, and if theirs is better, we dump ours. If ours shows comparability here and an improvement, we move to the new protocol. That's how, or we replace the old one. That's a way to go forward. But you know, if you're measuring wind speed at 2 meters, and I'm measuring it, this is a trite example, but you know what I mean. You're measuring at 2 meters, I'm measuring at 1 meter, and I'm saying that at this speed, this much sand moves, and you're saying at this speed, that much sand moves. We're not talking about the same thing anymore. So, and there are a lot of more subtle examples in that. This is the notion of protocols just establishes a basis for comparison. If you look at that paper by Martin, where they deconstruct the time averaging, and we've done some of this as well in the old days, your estimates of shear velocity or transport can vary hugely compared to other variables that you're measuring, just as an artifact of what time period you use to average.
Yeah, I would just follow up. I agree with you completely. And I would just follow up that there may be an opportunity for us collectively through the leadership of maybe Mike and some other people in the executive of ISAR to think about developing a set of protocols and standards that we might all adhere to. And so if we, you know, organized a couple of workshops where all the experts come in and think through all the kinds of issues that are involved, because a lot of these, as you well know, are relative. So, you know, how far, what's the appropriate fetch length? Well, you just can't use a number. It depends on the wind speed and the grain size and a range of other issues, right? So to establish a set of protocols, which we might then all adopt in future measurements. And as you say, you know, those protocols may evolve over the years, but it would be an interesting exercise to have us all join in and think about how we do that.
I agree. I think one of our challenges, one of the inertial issues in the Aeolian community, at least the field guys mainly, is that, and I'm looking at a lot of young faces here, and I don't know all of your backgrounds, but my guess is that most of us were not trained in this field. Many of us came out of coastal geomorphology. I see lots of coastal people here. Others may have come out of arid lands, not sand transport in particular, but studying dunes. And so we've come into this without having the formal training in an Aeolian science discipline, if that makes sense. And you know, some of you younger people can tell me if your training was substantially different from ours. But you know, I'm seeing a lot of faces from you guys that I've seen for a long time, and I know where you came from, and it wasn't studying windblown sand. We all just wisened up in our age. So Bernie, yeah, I think let's dump that on somebody else, man. But good idea.
I have a question to follow up, Doug. This is Christy. You know, I think with these protocols, that's ideally what we want to move towards. But I think one of the issues, and I'm curious to how you would respond to this, but the advancements in field observations have just really skyrocketed, especially over the last 10 years. And so in comparison to what you guys were doing back in the 80s is totally different from what is happening now. And so with these advancements, I'm curious if we can go too far to where it no longer actually matters, and these protocols might be really difficult to adhere to.
Well, I think that's a great point. And when I think of some of the things that we tried, it's just hard to imagine how naive we were and for how long. But this also, I think, goes back to Bernie's concern. We can't see, if we do adopt protocols, we can't see them as being fixed things. They will have to evolve. As technology evolves, it gives us ways of dealing with this. Think about how we process ultrasonic anemometer records. I love the ultrasonic anemometers. They're just a joy to use compared to the cup anemometers. How long do we average? What are the correct elevations? And we know there's a correspondence between wind speed and elevation and averaging intervals. But we don't get the same answers. Does that mean that all the cup anemometer data are wrong? Or is all the sonic anemometer data wrong? And in fact, they can't be wrong. They just are what they are. So we have to assume that as we go through this, that our field techniques and the way we analyze data will continue to evolve, just like we've evolved from handheld anemometers and I can't remember the Leatherman traps, right? Burying pieces of PVC and letting sand fall in. That's part of the evolution of what we're trying to do, and it has to continue.
I just have a comment. This is Robin. It seems to me that we have a lot of angst over measuring things that, 1 hertz or 0.1 hertz or something like that, and measuring the wind speed at some few centimeters above the bed and so on, and having sediment transport runs that last 10 minutes or maybe 30 minutes if we're lucky. And so there's a whole heap of errors that come into there just because of what we're trying to do. If we try to predict the amount of sand that moves from the beach into the dune on an annual basis, almost all of those errors go away. And we can actually measure the transport rate with all those wonderful new terrestrial laser and even drones, which Patrick seems to get into. And we got really pretty decent measurements of the total transport rate. And we just take hourly measurements from a nearby weather station, and that's it. We get rid of all this angst, and I can retire gracefully and not have to worry about it.
I agree with what you're saying and your motivation. That's an incommensurate approach to trying to understand blowing sand, right? Because when you're looking at transport into the dunes on a long-term basis, you're factoring in moisture content, slope, and vegetation. So in a particular environment, if your concern is for basically a sediment budget between beaches and dunes, yes, you don't even need to have an equation. You can do empiricism, right, and just measure. I agree. That's not the same as trying to understand the fundamentals of how wind and sand interact at, yes, maybe even trivial scales, because that's a basic physical problem. And when I was a graduate student, I remember being involved in one of these conversations. We were, for you geographers, you may recall this, Kristallers central place theory and the organization of cities. And my professor saying, no place actually looks like this, but this is what it should look like. And several of us arguing, well, if no place looks like that, what good does this do us? And his argument was, well, because if this is what it's supposed to be like, we study the departures from that. And that's what's important. If we could understand what the basic sand transport controls are and how they work, and we measure departures from that in the field, now we can tag them to something. Right? We can't really measure moisture content effects on sand transport because we can't measure the sand, we can't get the sand transport right. We can't really do sediment size effects because we don't know what they are. We can't do slope effects because we don't have that core model that we feel confident in. Maybe we'll never get it. But once we have that expectation, then the departures become departures from the ideal conditions rather than problems with our measurement, I think. I'm kind of a missionary for this, I know, but it's easy for me to say, you know, I'm looking at your lifestyle, Robin, and thinking it's really attractive.
I'm being a bit facetious in that, but I think we do need to look at what portions of the stuff that we measure at that very small scale are useful when it comes to measuring the medium to long-term scale, long-term time period and spatial scales. And I think the usefulness of the small scale one is it does tell us, I think we have a pretty fair idea of what are those sources of errors, the moisture content, the presence or absence of vegetation, the width of the beach if you're doing the coastal sort of thing, the interaction between airflow and the dune shape. Those are all things that I think we have a fair idea that they cause us a lot of grief. And so we can incorporate that into our mesoscale, but we don't have to worry about measuring those at that kind of scale. That's all I'm saying.
So Douglas, you know, as you know, being a guy who has watched a bunch of sand move around, but has no idea how it happens, of the 6 vexations, what's the worst and what are you going to do about working it out?
That's like, Patrick, which one of your children do you love the most?
Oh, that's easy.
I don't know. I don't know. I can tell you that after a substantial amount of effort, we have finally gotten some funding to do field work on granular electrification and to see if we can measure its effects on sand transport. So I'd have to say that's kind of my favorite right now, but it's only because I have some prospect of doing some work on it. But I think there's enough for everybody. There are enough things to do for all of us. Imagine this. If you had a breakthrough experiment in medicine, you would have dozens of labs around the world replicating step by step the experiment or trying to reproduce the results. In our, you know, if we go back to Bagnall's work or Kalamura's or Sorensen's or any of those guys with those early models or the current models, I can't think of an example, and maybe some of you know, where anyone has tried to replicate an experiment. We just don't do it. And in fact, I can't imagine going to a funding agency and saying, I would like to build Bagnall's wind tunnel, or I would like to go back and recreate those classic Castroville experiments from the 80s. There's no, I just can't imagine anybody saying, sure, that sounds like a great idea. So we're forced to kind of wander on from project to project, from wind tunnel to wind tunnel, doing the best we can.
Well, you got 2 problems, at least. One is the Castroville experiments, the drugs are now far too expensive. And 2, you know, where are the tunnels, for example? Like they had 2 superb, huge wind tunnels here at Flinders and Adelaide, and they've been deconstructed and gone. And, you know, I suspect 3/4, maybe all of the tunnels except a couple are completely gone too. So even starting to, you know, get to the point of recreating some of those experimental conditions is near impossible.
Well, still a couple of very sophisticated, well, maybe only one in Canada, several in China, as you know. There are some sophisticated wind tunnels in Western Europe, the Netherlands, Denmark. I don't know all the places where those tunnels exist. They're not all gone, but yeah, you're right. A lot of them are gone.
Doug, it's Jean. You
Over.
started this talk by saying that you agreed or you were asked to do this because you were old or at the end of your career. Not really sure which one you said. And you also since then said that you see a lot of people out in the audience that are young and that you don't recognize. And that includes some of your former students and some of your academic grandchildren, as I said. So putting those two together and given the 6 vexations and all the conundrums and the incommensurability you've mentioned, what would the 40 years of experience that you have, what would you offer to all the young faces out there? And, you know, if you had 40 more years in your career, what would you do? Because there are people out there who have 40 years left in their career.
If you don't like this, don't do it. If you like it, do it. And if you like this, work with people that you get personal fulfillment from working with and intellectual stimulation from working with. As I tried, and again, I really wish I had time or could remember all those that have allowed me to suck knowledge and wisdom from them. I do see a bunch of them here, but I've never done a field. I'm trying to think before I say this. I can't think of a single field experience with these guys that I didn't look forward to doing when we started and enjoyed having done when we were finished and learned something from. Even the ones that at the time were so god awful that you just wished you weren't there. But surviving those becomes the experience. You know, when you first start out, you may be forced into collaborations with people that are hard to get along with. You can learn from that as well. You can learn you're never going to work with them again, or you'd rather not, or you can find the kind of people that you want to partner with. So it's finding that path that just inspires you so you can do it for a long time, and finding people that you want to work with. I can't think off the top of my head of anyone who worked by himself or herself for a long time period. You know, even Bagnold at time had collaborators. Not many, but some. But you know he wasn't doing all that stuff by himself.
Thanks.
Hey, Doug, I just have one more question for you. It's Bernie again. And others may not be aware of this, but you know, there's a special volume of Journal of Coastal Research that just came out on field work in the coastal sciences. And Doug and I and Brian Greenwood and a few others wrote an article on how things have changed since the 80s in terms of doing field experimentation. And that was directed to nearshore processes. I'm wondering if you might reflect on how things may be changing in the aeolian field specifically. And what I'm interested to maybe think about a little bit is whether we're in danger of losing that field experimentation, and for reasons that it's expensive, it can be, you know, we're all risk averse. Universities are risk averse in terms of taking students out. Certainly COVID time is unprecedented. But the other side is that computational fluid dynamics is so seductive now and it's easy to do from your desktop. And I'm wondering if we're getting whole generations of new students who are just, you know, like buying into that wholesale, and we don't have the field truth anymore.
Look what time it is. That I don't know, man. There are a bunch of issues here. In some countries, there is still apparently a lot of funding and a lot of interest in looking at fundamentals of windblown sand and applications of that knowledge. And I'll think about China in particular because of the blowing sand hazard, the dust generation by blowing sand, and incredible efforts to rehabilitate landscapes by planting bare dunes. So there's a huge interest there still. In the US, my feeling is that dust, perhaps deservedly, gets a lot more attention than windblown sand. Of course, what we've been trying to sell is the fact that if it gets a little bit warmer and a little bit drier, huge parts of the Midwestern US is going to be open sand again when the grasslands wilt and dry. I don't really believe that, not in my lifetime, believe that. And the other issue of computational fluid dynamics, it's an incredible set of tools, and the graphics are amazing. And I would feel better about it if those guys that were doing that calibrated it with field data instead of wind tunnel data. Same with the theorists who are developing these new models, because basically they're calibrating their computer models with data that we already know do not replicate the real world. So it's a multi-stage process. I'd ask some of our European colleagues, I really don't know what the situation is like for getting field work funded in Europe, although I know some of our colleagues in the Netherlands and in the UK have been successful, at least in the last decade or so. I don't know what the current status is. If somebody can jump in here, that would be cool. Or not.
I can jump in here, Doug from the Netherlands. Hi. Thanks for your talk. I really enjoyed it. I consider myself one of the new people in this community. And indeed, in the Netherlands and in Europe, we've acquired some funding for field work, and but it's still pretty difficult to make a very theoretical analysis. Our field work is mostly driven by application. For instance, in the Netherlands, it's very urgent now to study the growth potential of dunes in the framework of climate change. And so funding agencies tell us, please go out. But the very fundamental work seems to be difficult to fund.
Well, I can share this, that when Bernie and Carl Nordstrom and Paul Garris and I, and I'm not sure if Robin was there for the very first Aeolus experiment or not. If you weren't there for the first year, certainly the second year. We had a very applied project in mind, and that was to look at the contribution to a coastal sediment budget caused by erosion of the beach by wind and dune growth. And we designed what we thought would be a sign. And by the way, we thought this would be easy. We'll measure some wind, we'll trap some sand, we'll apply the Bagnall equation, and we'll get out of there. Right? That was in 1987 or 88. Right? And we're still at it. 30 some years later, we've not gotten past that initial frustration. But we found ways to tie these little more, I hate to use the word pure science, I don't like that term, but more science onto an applied project to get papers published, or to have a graduate student do her or his research. So there's always something that we can do to leverage the opportunity to do the field work into something that we like better than just the application side of it. We have to fudge, and I'm sure you guys do that as well. Do you want to call it, Mikey?
It's up to Jean, Doug, but I've just relished every word. It's been a wonderful experience listening to you. I note that there are, 2 generations here and then a number of people in between. And I worry sometimes that we don't hear enough from your generation. And this has just been a wonderful opportunity, and I look forward to doing it again. Thanks so much, Doug.
What I will say in conclusion is I don't recognize a lot of you guys, but I recognize almost all of your names because one of the benefits of having done this a long time is I keep getting sent your papers to review. So it's a pleasure to see you guys. And again, I'm so grateful for the chance to talk about something that's clearly near and dear to my heart. And for those of you that I have done field work with or other, it's great seeing you guys again. And it's great seeing the beards, Slattery. I don't think I've seen that on you before.
Douglas, I shaved this morning just for you.
Okay. Thanks, y'all. I really appreciate the chance.
Thank you, everyone, for joining us. Thank you to ISAR. We'll look forward to announcements and to getting another one of these going. Right, Mike? Thank you, everyone. Thank you, Doug. Be safe. Adios.